Circuit Components Overview Motor Control Systems. Welcome back. In this video, we'll walk you through the essential components of a motor control circuit. Whether you're a beginner or brushing up your skills, this breakdown will help you understand what each part does and how they work together. Introduction to circuit segments. Motor control circuits are generally divided into two main parts, the power circuit and the control circuit. The power circuit is responsible for delivering electrical energy to the motor. It includes components such as circuit breakers, contactors, overload relays, and the motor itself. These components are designed to handle high voltage and current, ensuring that the motor receives the necessary power to operate efficiently. The power circuit carries the main current that drives the motor and is built with safety in mind to protect both equipment and personnel. On the other hand, the control circuit manages how and when the motor operates. It consists of low-voltage devices such as push buttons, selector switches, timers, relays, and auxiliary contacts. These components send signals to the power circuit to start, stop, or modify the motor's operation based on certain conditions or user input. The control circuit enables automation, interlocking, and protection features, allowing for more precise and reliable motor control without the need to directly handle high-power components. By separating the power and control functions, motor control circuits enhance safety, simplify troubleshooting, and provide greater flexibility in system design and operation. Power Components Overview. 1. Circuit breakers. Circuit breakers are safety devices designed to protect electrical systems from damage caused by short circuits and overloads. In the event of an overload, when electrical equipment draws more current than it is rated, the circuit breaker monitors the flow of current and detects when it exceeds a preset safe limit. Similarly, during a short circuit, where electricity takes an unintended low-resistance path, the current rises sharply and dangerously within a fraction of a second. When either of these fault conditions occurs, the circuit breaker automatically interrupts the electrical flow, disconnecting the power supply to prevent overheating, equipment failure, fires, or even electric shock. This automatic disconnection not only protects the motor and wiring but also enhances the overall safety and reliability of the electrical system. Once the fault is cleared, the breaker can be reset manually, restoring power without needing to replace any components, unlike a fuse, which must be replaced after it blows. 2. Contactors. Contactors are electrically operated switches used primarily to control electric motors and other high-power loads. Unlike manual switches, contactors are controlled remotely using a low-voltage control circuit, making them ideal for automation and safety. They consist of a control coil and a set of electrical contacts, typically including normally open NO and sometimes normally closed NC contacts. When the control coil is energized, usually by a signal from a push button, relay, or control circuit, it creates a magnetic field that pulls the contacts together. This closes the power circuit, allowing electrical current to flow from the power supply to the motor or load. When the coil is de-energized, the magnetic field collapses and the contacts spring back to their normal open position, stopping the flow of current and turning off the motor. Contactors provide several advantages. Remote operation, they allow switching from a distance. Electrical isolation, the control circuit is electrically isolated from the power circuit. Safety, contactors can be integrated with overload relays and emergency stop systems. Durability, designed to handle frequent switching under load. In summary, contactors are essential components in motor control circuits, enabling safe and reliable operation of electric motors by switching high power through a low-voltage control signal. 3. Overload relays. Overload relays are protective devices designed to safeguard electric motors from damage due to excessive current, which can lead to overheating. Unlike fuses or circuit breakers that react instantly to short circuits or large current surges, overload relays respond to prolonged overcurrent conditions that are just slightly above the motor's rated capacity. These devices are typically installed in series with the motor and work by monitoring the current flowing through the motor conductors. If the motor draws too much current for an extended period, often due to mechanical overload, a jammed load, or low supply voltage, the overload relay will trip. When the relay trips, it activates its internal contacts, usually a normally closed contact in the control circuit, which in turn interrupts the control circuit and energizes the contactor coil. As a result, the main power supply to the motor is cut off, stopping the motor before it can overheat and sustain damage. There are two main types of overload relays. Thermal overload relays use a bimetallic strip that bends with heat generated by current flow. If the strip bends too far due to excessive heat, it trips the relay. Electronic overload. Relays use sensors and microcontrollers to detect overcurrent conditions more accurately and provide adjustable trip settings and advanced diag. Overload relays are a critical part of motor protection and are typically combined with contactors in a direct online (DOL) starter. Together, they help ensure that the motor operates safely within its rated limits and is shut down automatically in the event of an overload. 4. Motors. The motor is the final component in a motor control circuit, often referred to as the end device, and its primary function is to convert electrical energy into mechanical motion. This mechanical motion is then used to perform work, such as driving a pump, turning a fan, rotating a conveyor, or powering a machine. In direct online (DOL) starters, the most commonly used motors are squirrel cage induction motors. These motors are favored for their simplicity, reliability, and rugged construction. They have no brushes, commutators, or slip rings, which makes them low maintenance and highly durable for industrial and commercial applications. The squirrel cage motor gets its name from the appearance of its rotor, which looks like a spinning squirrel cage made of conductive bars shorted at both ends. When three-phase alternating current is applied to the stator windings, a rotating magnetic field is produced. This magnetic field induces current in the rotor bars, generating torque and causing the rotor to turn. Key advantages of squirrel cage induction motors include robust construction with fewer moving parts, low cost and ease of maintenance, high efficiency and reliability, self-starting capabilities when connected directly to the power supply. Because of their straightforward operation, squirrel cage motors are ideal for DOL starters, where the motor is connected directly to the full line voltage without any soft starting or speed control. This approach is well suited for small to medium-sized motors where high and rush currents are acceptable and where the load can tolerate sudden starting torque. In summary, the motor is where electrical control systems deliver their final output, turning electrical signals into usable mechanical energy, making it a critical element in any motor-driven system. Control components overview. 1. Push buttons. Push buttons are manual switches that control the operation of a circuit. The green NO button starts the motor and the red NC button stops it. 2. Selector switches. Selector switches are used to choose between different modes, like manual or automatic, or forward and reverse directions. Auxiliary relays. Relays are similar to contactors but used in control circuits. They allow low-power signals to control multiple outputs. 4. Timers. Timers delay the operation of a circuit. For example, a timer might start a motor 5 seconds after pressing the start button or turn it off after a set duration. Fuses. Fuses are protective devices designed to guard electrical circuits and equipment, such as motors and control panels, against short circuits and severe overcurrent conditions. They are simple yet highly effective components that operate on a very basic principle. They contain a metal wire or strip that melts when too much current flows through it. Under normal conditions, current flows safely through the fuse. However, if a short circuit occurs or the current suddenly spikes well above the rated level due to a fault, the heat generated by the excess current causes the fuse element to melt or blow. This breaks the circuit immediately, stopping the flow of electricity and preventing damage to downstream components like contactors, overload relays, and motors. Key characteristics of fuses. Fast-acting protection. Fuses react almost instantly to fault conditions, making them highly effective for preventing equipment damage. Single-use devices. Unlike circuit breakers that can be reset after tripping, fuses must be physically replaced once they blow. This can result in longer downtime if spares aren't readily available. Simple construction. With no moving parts or electronics, fuses are extremely reliable and resistant to mechanical wear. Cost-effective. Fuses are typically inexpensive, making them suitable for low-cost protection in a wide range of applications. Fuses are commonly used in DOL starter circuits, particularly in the power circuit, to provide primary protection against faults before they reach the contactor or motor. They are usually rated for both voltage and current and must be carefully selected to match the motor's characteristics and the application's safety requirements. Limitations. Must be replaced after operation. Offer no indication of the fault cause or condition unless combined with external indicators. cannot be remotely reset like circuit breakers. In summary, fuses act as the first line of defense in motor control systems, providing critical protection against dangerous overcurrent events. While they offer reliable and rapid protection, the trade-off is that they require manual replacement after each fault event. 2. Emergency stop, e-stop, systems. E-stop buttons provide an immediate way to shut down machinery in an emergency. These are usually normally closed and wired into the stop circuit for fail-safe operation. Sensors and actuators. Sensors detect physical parameters like position, temperature, or pressure. Common types include limit switches, proximity sensors, and temperature sensors. Actuators. Actuators perform actions like opening a valve or moving a part based on control circuit signals. Summary and component interplay. All these components work together in a motor control circuit. The control components decide when the contactor energizes. The contactor then allows power to flow through the protection devices to the motor. The entire system must be designed with safety, efficiency, and reliability in mind. Now you've got a solid foundation in the basic components used in motor control systems. In the next video, we'll look at how these components are wired in a direct online starter circuit.